Today I'm happy to talk to you about a very interesting, hopefully interesting subject, which is how do we see, right? We see things every day, right? We see things and we feel. Our visions will fill us with emotions, right? What's happening there? I'm a chemist, so I will be using the language of science instead of art. So I will try to give the talk in a way that can be at least understood and appreciated by non-scientists, non-scientists, anyway, by people who haven't studied science. But sometimes I will carelessly slip in some sciencey terms, right? It's unintentional. It's just like an American, when in conversation, they would sometimes give us cultural references that is kind of couldn't be understood by other people outside America. If I do that, if you catch me do that, please stop me, right? Otherwise, I will start kind of branching out into kind of random talks about science. So I would like to do two things in this talk, achieve two things in this talk. The first thing is very easy to do. The second thing is quite difficult. By the end of this lecture, I hope you will appreciate that we have a concept that the way we form visions and emotions derived from vision is all to do with chemistry and structure, right? People said biology is all to do with function and structure, right? Interplay between function and structure is actually it's not unlike architecture or artistic thinking. This is the first point. The second point is so that's the easy bit. The difficult bit, the difficult kind of intended outcome of this lecture is, by the end of this lecture, I hope you will appreciate as much as I do that life is really amazing, right? So that's the difficult bit. Well, let's see how it goes. I'm sure this is starting point of everybody's kind of ideal vision, right? In a way, it's kind of a very 19th century way of thinking. Like human is a machine and kind of anatomy is engineering. And so basically, it's kind of an image that I captured from Google. And basically comparing our eyes with the camera and I'm sure you have seen this kind of comparison that our eyes is a CCD camera, but our eyes is like 4 billion years old, and this is like 40 years old, and that sort of things. There's similarity in anatomy, in structure. They are both kind of devices. It's got a lens, right? That kind of focus light onto a chip or retina. And then image of form, right? So the basic optics. But if you think about it, the comparison between the camera or your iPhone camera or kind of your beautiful, expensive camera, either it's film or CCD camera, with human eyes is actually quite superficial, because what the camera do is to record an image, right? Basically a 2D array of pixels. That's it, right? That reflect the kind of the environment. So environment capture on a 2D array of pixels. But then we need a brain to look at this pixel to interpret, right? So therefore, the similarity between the camera and our eye is the formation of this pixel array of pixel. But this pixel without the brain is completely meaningless. So therefore, this lecture we're going to spend kind of maybe the beginning 1/3 to talk about this structure, and the rest of the lecture is talk about a much bigger and much more meaningful and important organ in seeing, and that organ is the brain. So in a way, kind of the purpose of this slide is to show you the visual organ, kind of the structure in our body that is responsible for seeing is actually much bigger and much more complex than we thought. We thought is the eye, right? But then this whole thing is actually the structure for seeing. When you see a painting that touch you, when they see a movie that completely moves you, you're not using your eye. In fact, your eye is just a device that turns these images into 2D array of pixels. It's the brain that's doing all the job. Is it okay? This kind of. Are you? By the way, are you comfortable? Are you too cold or too hot? Or is it okay? Okay. So if you agree with this kind of journey, let's start, right? So unfortunately, I don't think the remote control works like it. So scientists are kind of reductionists, right? We are materialists. We want to touch things, and so basically, for us, in order to understand something, we need to be able to see it, to touch it, right? So it's a human eye, right? So basically, imagine you have a human and like Jackie Chan movies, and they're fighting, and sometimes there's a move, right? You can kind of pick out somebody's eye, right? And without your opponent even knowing it. So imagine that thing. So it's a human eye and it's cut in the middle, right? It's a very, very scientific approach, right? You don't understand something, you just cut it open in the middle and see what's inside, right? So, and of course, this is, if you have kind of studied biology in high school, you probably have kind of done these experiments, right? Cutting an eye open. So you have a lens. So in a way, it's almost like a camera being opened up, right? There's a lens and there's a gel inside, right? And the gel is kind of another story that controls the reflective index of light. It doesn't matter. What I want to draw your attention to is the kind of the back of the eye, and you can see there are two layers, right? In the back, there's a very, very black layer. In English, it's called pigmented layer, right? It's actually the blackest skin in our body. Right, in anybody's body, it's actually it's the blackest of black. Some scientists a few years ago has invented the blackest color, right? And it was actually used in the artwork or kind of in sculpture. It's something like that. It's not as black as those sculptured color in the sculpture, but it's the blackest of black skin in anybody's body. On the top of this pigmented layer, there's a layer called retina. When scientists doesn't know what things work, they will cut open, right? And then they will look, right? They will look closer and closer and closer until you almost can smell the blood in the eye. But then if it's not enough, you put it under the microscope, right? So that's what people have done. And this is actually the side view. So if you take this retina, which is a kind of a whitish layer with a piece of chopsticks, right? You can actually easily peel it off. So basically, the pigmented layer will come off, right? Together with this retina, with the kind of peel it off. And then if you look at this sheet of black and then black in the bottom and white on the top, sideways. So it is how it looks like, right? It's a structure. It is by using a technique called electron microscopy, scanning electron microscopy. So our department has just bought a new one, and if you want, you can actually I'll show you, right? So and this is the side view, right? So the pigmented layer is on the top, the whitish retina is on the bottom. So the direction of light is actually from now. The lens is now on the floor, right? So. And then you can see that these kind of layers, the whitish layer, are quite complex, right, in their texture. And their complexity, kind of their form, is they're made up of vertical lines, right? So, in fact, you can use a chopsticks, but this time very, very small chopstick, nano chopsticks, and pick up the pigmented layer and peel it off, right? So you can do that, and this is how it looks, right? So now it is an exposed retina, the whitish layer, without the pigmented wall. So now you can see that those kind of vertical lines, without the support in the back, they become loose, right? And they're like noodles, right? So basically, our journey starts from this noodle, right? Start from these noodles. The light came from the bottom, the lens is on the floor, the pigmented layers on the ceiling, and now between the ceiling and the floor, there are these noodles, right? And if you zoom in, and then we find that these noodles are cells, right? And they are so-called photoreceptive cells, meaning that scientists, they love to use these long words to intimidate people, right? Photoreceptive cells are basically cells, you all know about cells, right? That receive light, right? So there are two types of photoreceptor, but I don't want to kind of complicated things. Let's say the difference between the two types of cells for another day. So these noodles are actually very, very long cells, and this is the kind of artistic, kind of simplified, well, not artistic, but almost like a design structural architecture diagram of these long cells, right? There are two types, but we don't care about the two types today. There are two parts of these cells. The upper part are very strange things. They're almost like a battery, or kind of like a column with horizontal lines, stacks of horizontal lines, right? The bottom are kind of other part of the cells. For today, we don't care too much about the structure of the cells and things like that. Let's just say that the upper part are interesting. The upper part, the part with the stacking layers, are the interesting part, because these stacking layers are what make this photoreceptor unique and essential for image formation. The lower part are the machine rooms. They are the part of the cells that keep the cells alive. They're kind of the surface room, the machine room, or the kind of machine plant, the back of the house, the kitchen, you can imagine. Today we don't care about this back of the house stuff. We care about the upper part. So if you keep looking, right, this is no longer, it's also a diagram to show in three-dimensional the upper part of these cells. So once again, it's like a rod. In fact, you may not, it's not important. These cells are called rod cells because they just look like a rod or a chopsticks. And then if you zoom in, right, and then you eventually remove the cell membrane, and you see stacks of membranes, right? Those are the horizontal stacks of membrane. And these membranes are the kind of really, really amazing nano machines for collecting light. Comparing the solar panels on the kind of on the roof of this building or other buildings, this is 1 billion years more advanced than any solar panels that can be created by human engineers. But the basic idea is the same. It's to collect light, turning light into energy. So, what it does, so basically you kind of mentally strip off the rest of things and just look at these horizontal stacks, right? And then we find that it's just like a machine. It's just like a solar panel. So horizontal because it's kind of perpendicular to the direction of the light, right? So the light will come down. So here above, I use the word photons, but once again, it's kind of unimportant, right? It's a sciencey way to make sure nobody understands. If you don't like the word photon, let's just convert this into light. But photons sound so much cooler, right? So anyway, so the light will come down, right? In a direction perpendicular to this surface, and on the surface there are nano machines, and these machines are represented here as green and pink dots. Each dot is the size of one molecule, right? But what this dot does is that the green dot will collect the light, and I will tell you how it does that in the next slide. But the energy collected by the green dot will be given away to the pink dot. So they have a kind of a photo antenna, right? The antenna is green, and then the antenna will capture the light, photons, and then distribute the energy to the pink. So one more really cool thing. You may not think it's cool, but I'm a scientist, so I'm a nerd. I love these sort of things, right? So the membrane on which these nano machines are displayed are almost transparent. It's made of liquid, almost transparent. So the idea is you have this kind of solar panel, right? Photoreceptors, antennas in green. So the light will come, right? And each pocket of light is received by one green dot. But what if this pocket of light just just is not kind of captured by the green dot? So this pocket of light will penetrate down to the next layer, right? So that there may be some green dot just right in the path of this light will be captured. If it's not captured, it will penetrate to the third layer to be captured. So if you understand this, look at how many layers are these. Look at how many. Look at how many layers are these, right? Layers and layers, and to make sure this machine, this rod, this light sensing cells is able to capture even the smallest unit of light. The dimmest unit of light, this machine can be captured. The smallest unit of light is called a photon, right? And we now know that this nano machine in our eyes, each of these machines is able to capture one photon. You can't get any more sensitive, right? That's because of the interplay between structure and, but I'm a biologist, I hate to use the word design, right? In evolution. It's caused by evolution that make this structure perfect for capturing low light intensity. It is important, right? Imagine you're not human, but you're kind of the ancestor of human, and you're the little primate climbing the tree, right? And basically you have down the tree, you have tigers and lions and everything whose life purpose is to eat you. Your only chance to survive is to be able to see things in the dark, right? This allows you to capture even one photon, the smallest possible, the dimmest possible light, right? We're here sipping coffee and kind of listening to talks thanks to this, right? Because without this, we have been extinct 5 billion years ago. Sorry, not 5 billion, but maybe 500 millions. It doesn't matter, right? I'm a scientist, so this sort of numbers is important. Okay, so now this gets really, really sciencey, right? But it doesn't matter. You're not supposed to kind of even understand this slide. I just want to tell you this green dot, right? The green dots capture light, right? But what does it mean by capturing light? So what happened is, so basically this is the green dot, right? So this green dot is the size of a molecule, and this molecule is made of protein, which even doesn't matter. What I want you to imagine that this light captured molecule is like a hand, right? Basically a hand holding a black chemical compound on the palm. So in a way, the function of the hand on this slide is the blue thing, is to present this diamond, the black diamond, black jewel. That is the only important part in this whole slide to the slide. In each layer, there are many hands holding this dark diamond towards the light, holding it up towards at the best possible angle, right? So each green light each green dot on the previous slide is a hand holding this black molecule, and this black molecule is called retinol. This is retinol. Scientists want to kind of confuse you by giving you new names. It's not. Another word for this is vitamin A. Vitamin A from carrots and your mother said, please eat your vegetables, otherwise you'll be blind. That's because of this, right? This came from, our bodies cannot make it. This came from vegetables. So basically, we eat vegetables, our body digests the vegetables, and then our body will extract this molecule, these black molecules. The blood will bring this molecule to our eye, put it in the hand, the blue molecules, and hold it to the light. That's it. So if you understand this vitamin A, there are two forms of vitamin A. One is called cis and one is called trans. Scientists love this kind of words because it kind of sounds cool, right? We are very, very lonely and we are very uncool, so we invented this word so that we can talk to people in bars. It doesn't matter. Cis means band, chance means straight, right? So these molecules are usually bent. If light penetrate into the cell and captured by the green dot, this machine, nano machine, the light, one photon, is enough, will give you enough energy to straighten, to convert the bent vitamin A to straight vitamin A. That's it, right? And this conversion promoted by light is the secret of light detection. So now, basically, light absorption will convert the bent form to straight form. So once it's straight, if you switch off the light, it can't go back to bend again because you need another kick, right? You need another energy. This energy, because there's no more light, so then it's just one off, right? You can switch on, you cannot switch off. It's kind of uncool. So our body we evolve something that can switch off. We evolve a off switch, and this switch is an enzyme. Light will convert the bent form to straight form. It's done by physics, spontaneous reaction. But if there's in absence of any light, no outside energy, our enzyme will convert this back to the original bent form, so that this machine is ready for another round of light collection. This kind of process is very quick. Very quick. It takes a fraction of a second for this cycle. Light switch on, and then enzyme switch off in the absence of light. Only take a fraction of seconds, but because it's kind of good enough, right? If you remember your ancestor, this living primate on the tree, the line is running to you, right? But no matter how fast the line is running to you, it cannot move faster than a fraction of seconds, right? But in 20th century, people invented movies, right? Movies, 24 frames per second, hectare, actually utilize this. This conversion is not able to catch up 24 frames per second, creating an illusion that some images is actually a smooth motion. I will tell you more about that, but this is kind of to me it's kind of cool, right? We are modern technology is kind of using our biology is not able to catch up. To be honest, the how fast people the image move, and this inability of catch up has generated a new art form. Okay, this slide is very sciencey, and I'm kind of showing this just to show you how cool we are, but it's not. You're not supposed to understand, right? If you don't like numbers and chemistry, just don't look. Right? It's not, but anyway, the idea is, so let's go through this one step by step, right? Here is a cell, right? That noodle you saw on the retina, and the upper part is the horizontal lines, right? So we know what we're still talking about these cells, and we zoom into one membrane, right? This thing, forget about this word. This thing is a green dot, right? It's a green dot. It's a hand that holds the molecule. It's the hand, and this is the molecule. Now it's bent, right? And forget about all these things. These kind of sciencey things. They will give you a few Nobel Prizes, but it doesn't matter, right? But the most important thing is when this cell is alive, when it even is dark, this noodle cell, this kind of more fantastic nano machine, is still working. Even though there's no light, it's still using energy, and it's actually doing lots of things that is not important for today. The only important thing is this word, glutamate. In absence of light, this cell is still busy working, and what it does is actually pumping a chemical called glutamate from the inside of the cell to the outside of the cell, thereby keeping the concentration of glutamate at a relatively high level in the extracellular space around this machine, these cells. It's kind of very sciencey, right? But I hope by the next 2 slides you'll get a better understanding. By the way, glutamate is kind of the chemical component of MSG, right? Monosodium glutamate. You go to a Japanese Chinese restaurant and then they put tons of it. This stuff. So when there's light, the hand's holding this molecule, right? It's still there. Now this molecule is straight because one photon is enough to convert the bent molecule to straight molecule. A lot of things happen. It doesn't matter. And then what happens is the only thing we need to care today is a lot of things happens, and that leads the cells to shut down the secretion of glutamate, right? So therefore, these cells, when there's no light, busy working, pumping glutamate in a steady rate to the immediate surrounding of these cells. And then whenever there's light, the excretion of glutamate is shut down immediately, so that the immediate concentration of this compound around these cells suddenly slow down, right? And of course, when you switch off the light again, there's no energy, right? There's enzyme coming here to make the straight protein bend again, and thereby restoring the situation of these cells to the darkness situation. The enzyme will bend this molecule, everything going back, and now the secretion of glutamate increase again, right? Light decrease, no light increase, right? So the idea, therefore, what happened is the noodle, the eye, the retina, the noodle, each noodle act as a controllable light-sensitive pump of glutamate, and thereby converting light signal into a chemical signal, right? It's very, very sciencey, but it's like that. If you have a retina, right, the retina is full of cells in a 2D array. Well, it's kind of a concave, it's not really 2D, it's a concave array, but if you kind of open up and then kind of push the eye like that, and then it becomes 2D, right? 2D array, and if you have a laser pointer, and spot your laser in one of the cells in the middle of this 2D array, this cell will suddenly molecule stripping up, right? Glutamate excretion shut down, and glutamate suddenly become this dark, means lower concentration, right? So converting a local light, a local distribution of light to a local distribution of chemicals. That's what your eyes does. What is? So now we kind of zooming out, right? We're talking about nano machine. Let's zoom out again, and here's the eye again, right? This kind of a concave array of cells. And now what I told you about this glutamate concentration and light sensitive and hand-holding molecules that got straightened up by light happened within each cell independently, or almost independently. And basically, what you're doing is, these cells are almost like pixels on your CCD camera, and the light will cast a shape or cast an image of this chip or array of cells. Each cell responds to the light level in immediate surroundings, and then generate a map of chemical change that represent the light, the image, right? We have about 200,000 cells per millimeter, but by the way, the distribution of these cells or pixels is not uniform, it's not even in our eyes. In the densest place of the eyes, the kind of the focal point of the eye, the densest place, we have this number of pixels per milliliter. There are about 1 to 200 million pixels or cells in the entire eyes. There's about 1 order of magnitude more than a CCD camera, right? So basically, you probably say that, oh, we are better than CCD camera because our eyes have better resolution, right? I think we're still better, maybe for the next 6 months, and then the engineer will come up with. We don't know, but the concept is image casting on retina, individual cells in retina respond to the light and translate this image into a distribution of concentration, chemical concentration, right? Is it okay, or is it mildly interesting, or so this is for most lecture about looking at things, that's the end, right? Because that's what camera do, right? Converting an image to a 2D array of pixel, that's the end, right? But what I want to tell you is this is only the beginning of our journey today, right? We're not even outside the airport yet. That's the metaphor. So the next step is, so it turns out that retina, this kind of whitish layer that you pick up by a chopsticks, contains more than one layer of cells. The bottom layer, this is called so this layer, you can still remember this kind of long rod shapes, right? This is the back of the house, and this is the kind of the stacks of membranes holding these photoreceptors, right? So this is actually what we're talking about. And now we're stepping outside of these cells. They're actually two types, but we don't care too much about them today. We're actually stepping outside these cells and move towards this layer. These names are neurons. They're nerve cells responsible of connecting your eye to the brain, right? Because today we are talking about eyes and brains, these are the highways from the airport to your hotel. I wanted to spend more time on these highways because it's actually more interesting than just kind of a channel for transportation of signal. So, it's very, very sciencey. The discovery of this kind of map has got a Nobel Prize, but it's not important, right? Who cares about these sort of things? There are many, many words, none of them are important. I will only tell you one thing on this slide, about this slide. We only care about one thing. That thing is as follows. These are the photoreceptors, these are the solar panel, these are the input, right, so to speak. These are the input. These solar panels will convert light images into distribution of chemicals, right? You still remember that. And these are the input, and this kind of are the output. This will go out to the optic nerve that connect your eye to the brain. When you see Jackie Chan killing people, he will pick out people's eye, right? I can't remember the name of this move, but you can just pick out people's eye. So the eye just didn't come out like a ping pong ball, right? There's a ping pong ball with a kind of cable, right? And sometimes the victims will have the eye hanging, right? That cable is an optic nerve that connects the eye to the brain. So the only point I want to make on this slide is there are far more input than output. It's a semantic diagram, but you can actually see the point, right? Here there are 8 input, 8 photoreceptive cells, and there are only 3 output. This highway, the function of this highway is to cut down the number of signals so that your brain will not be exploded, right? It simplifies the signal in a way without losing information, right? In a way, simplifying the signal without losing information is what a computer does, right? It's an algorithm. Before the signal even leaves our eyes, there's actually a very, very advanced biological computer doing the first run of computation and send the data, the result of this computation to your brain, right? So, I will tell you why, and it's really, really like a computer. So please be patient, right? Because it's kind of, we will take some kind of step-by-step explanation. So, these are cells with many different names. If you have more input than output, then a logical conclusion is this input will join together, right? So this is exactly what happened. So you have this input, and then this input will, and then you have actually a cell. Each cell is connected to 2 input, right? It's called bipolar cell, but it doesn't matter. And two bipolar cell will be converted to a cell called ganglion cell, right? So basically input and then summary of inputs by one cell type, and then summary of the summary by the second cell type. There are some strange cells called horizontal cells that actually kind of run across multiple input. But the idea is input joined together into a single output. Exactly how the multiple input are joined together in a single output, we still don't know. We only know the basic principle, but exactly how many cells are joined together, how they are joined together, what's the relationship between the way these cells are presented on the presenter in a 2D array and how they join together, we still don't know. Some people said this is actually one of the most important questions in biology, the way how these cells are connected together. Because as a biologist, without knowing how they are connected together, we will never understand exactly how this computer works. Okay, but this is the best we can do, right? But so we have photoreceptors, input, one layer of summary by bipolar cells, and then the summary called, and then another layer of summary called ganglion cell, right? So you understand now the logic, right? There are many ganglion cells in our eyes. Each ganglion cell collect information from a large number of photoreceptors through bipolar cells. We call this organization. So basically now, if you have a kind of summary diagram, this bipolar cell and then the several bipolar cells will join together into a ganglion cell, right? So let's look at the bipolar cells now. So we have each bipolar cell receive information from a number of photoreceptors. So this group, and then the next group will also join together and join together. So and then this kind of is almost like water funnel, right? Water collected from different rivers, right, into a reservoir. The reservoir is a ganglion cell, and now each reservoir kind of is responsible for a number of rivers, right? And the river cover a certain area. That's kind of the water example. And that area, the area that corresponds to a reservoir, ganglion cell, is called receptive field, meaning that that ganglion cell collect data from a field of light on a retina. So now, and the receptive cell can be divided into two zones. One is called center and one is called surround. These sort of things are discovered by American scientists, so they always misspell this as center. So if you do Google and read, they always use center, but I changed that. But anyway, it doesn't matter. The receptive cell is kind of the receptive cells, all these signals are entering the ganglion cell, can be roughly divided into two zones, the center and the periphery, right? It turns out that there are the ganglion cell, so basically the ganglion cell is sitting downstream. This ganglion cell is very, very clever. This ganglion cell is not only receiving information like chemistry distribution on this cell by cell, the chemistry distribution, the distribution of glutamate are different, but they can also tell if the chemical of glutamate has a lower concentration in the center than the outside. Imagine that, remember that glutamate concentration reflects light intensity. If there's light, there's lower concentration of glutamate. So if this ganglion cell, now he's sitting there receiving information from a large number of cells, and he or she knows which cells are in the center, which cells are in the periphery. Then this cell will do very, very simple calculation or sensing. If the cells in the center have lower glutamate concentration than the cell in the outside, this means that in this the light distribution of this receptive cell is not uniform. In fact, there are more light in the center than outside. Which means that this little computer is now summarizing this individual pixel distribution into an information of gradient, right? So, a cell is a neuron, right? What neuron does is to send electric signals, right? The way the signal is not like on and off. In fact, neuronal signals are very, very interesting. Even though the neuronal cells are not doing anything, are not so-called excited, but still alive, it will still send out signals. The signals are like a Morse code. They are pulses of signals. Instead of one continuous signal, increase or decrease, the strength of the signal is always the same, but it's a duration that's different. For biologists, we kind of we don't want to be lazy, right? We don't want to we use graphic to represent this phenomenon. This graphic is this time. This horizontal axis is time, and this vertical is register the pulse of the signal, right? It's the signal, the meaning of the signal strength is always the same, and the meaning is conveyed by the frequency of the signal. So if this pulse is very, very fast, means that this cell is excited. When it's very, very slow, means it's not excited, right? So the signal change over time. Now, this is actually the signal of that ganglion cell. It turns out that this ganglion cell collects information of light distribution in each receptive field. If there's more light in the middle than outside, we call this center ganglion, right? Meaning that these cells will be excited if and only if there's more light in the center than the periphery of this receptive field. If this receptive field, the light is uniform, this is not excited. If this receptive is equally bright or equally dim, not excited. Only if the center of the field is brighter than the outside, is excited. It's excited by firing more rapidly. There are another type of ganglion called off-center ganglion. And it's actually the same cells, but it works opposite. So it will also collect light from receptive area, but it will fire, it will be excited, stimulated only when the light intensity of the center is dimmer than outside. There are two types. It's almost like your eyes, this computer, cannot decide whether there's more light, the light distribution, by only one guy, right? They need two persons to tell you, and these two persons sense things oppositely. If the signal given by these two commander or two computer are consistent, agree with each other, then the computer will say that now I agree that there's more light in the center than in the periphery, right? So it's kind of a safeguard kind of a strategy in our biology. So now we are back to this graph, right? Retina and noodles and individual cells converting distribution of light into distribution of chemicals, and the ganglion cell convert this distribution of chemical, the gradient of this chemical, into electronic signals. And therefore, if you look at the image, so this image projected on your retina, this is the cell's chemical signals. One pixel, each pixel responds to light differently. And now, this signal is processed by the ganglion cells. Each ganglion cell is responsible responsible for one receptive field, and the signal from one cell will give you this information, right? Is it okay or too far? Now, if it is okay, then the question is, this is nice, right? This high resolution image, better than the best CCD camera now. This is shit. I'm sorry. This is not good, right? Because by cutting down the amount of information, you lose resolution, right? But our biology is very, very clever. Because, once again, I'm going to take 1 hour to explain this line. We're not going to explain this line. The only point I want to make by using this information is these receptive fields are not separate, are not mosaic, right? But they're overlapping. They are overlapping very, 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 very redundantly. Each field, each kind of area, each zone on the retina is kind of the data from each zone, the refractive field, is kind of computed by a large number of overlapping fields. If you have a large number of overlapping information about the gradient of something, then you can actually retell the image with the same resolution, but now converting from distribution of pixel to overlapping distribution of gradients. Is it okay? Or for chemists and biologists, they couldn't understand this, right? But I think you guys are artists, most of you, and you are very, very visuals, and to you, it comes to you naturally. My friend Hector has a brilliant show last month, and when I saw his show, I almost cried because he's an expert in, I'm sure many of you know him, he's an expert in visual perception and digital art. He's an artwork called approximation theory. In a way, the spirit of the artwork is a wonderful, perfect demonstration of what I just told you, converting pixel into gradients, overlapping gradients. But the way this gradient overlap redundantly will give you the image, will form the image. So Hector's actually used basically images of overlapping gradients, right? And increasing number of overlapping gradients will actually give you an image. If you keep on increasing the number of gradients, you will end up with a very, very highly resolved image of this guy, Jesse Owen, running and winning the Olympics. Is it okay? Or now, but what's the point, right? We have now two ways of representing an image, right? The first one is pixel, pixel, pixel. The second one is gradient, gradient, gradient. What's the point, right? Life, we don't do things for fun, right? So the idea is, the whole point of doing that is, the gradient, overlapping gradient, will give you the same image, the same resolution, information, but the amount of data is dramatically reduced, right? So now, you no longer represent the image as unrelated pixels, but you actually have a function that describes how these pixels are related to each other in different zones, and this function, computation, will dramatically decrease the dimension, the volume of data. So now, once again, it's what? Right? Machines, random machine hand-holding molecules, right? This is still what we're talking about. And now we have this kind of computer. The aim point of the computers are retinal ganglion cells. Retinal ganglion cell. Each retinal ganglion cell is responsible for one receptive field. They can sense whether the light on this field are even or uneven, right? They're on and off, so we're still talking about these same structures. And each is overlapping cells. Each cell is responsible for overlapping field, right? We're still on the same page. But now the new information is, each cell will send you one fiber. And this fiber connect your eye to your brain, right? That fiber will give you, or based on the gradient of the light on this receptive field, and this fiber is sending this Morse code from the eye to the brain. There are about 1.2 million ganglion cells. There are about 200 million photoreceptor cells, right? I told you before. This data is summarized into 1.2 million ganglion cells. Each ganglion cell sends out one fiber, right? So you have a bundle of fiber from the eye to the brain. Is it still okay? If you cut this bundle, you're blind, right? Is it still okay? And or in future, if you kind of connect this bundle to a machine, then you will see things, right? So, but now each bundle is from one cell, right? Your brain, and I'll show you in the next few slides, are is designed in an extremely precise way. Each bundle will give you 4 pieces of information. The first information, or 3 pieces of information. The first piece is XY coordinate of this cell on your retina, right? The first piece of information, each bundle, our brain will know the precise position of its respective field on the retina. The second one is whether this cell is on center or off center, right? Because it's important to know if you mix this up, then the image we see will be inverse, right? Will be like a negative. The second one is the signal strength. The signal strength will tell you whether this respective field is brighter in the center or dimmer in the center. So now, if you have this bundle, each fiber will give you different signal at different time, right? They will fire at different time, different strength at different time. Because of these 4 addresses, so to speak, or these 3 addresses in one signal, our brain will know exactly what is happening to the retina, and therefore what's happening in the outside world. The lion is coming, or a potential mate is coming, right? That's all based on these 4 numbers or 4 digits. So, it's a very sciencey figure, right? It doesn't matter. We know that this is the eye. This layer is the white layer retina on which there are noodle cells, so we're still on the same page. These lines are the fibers sent out by different ganglion cells, right? 1.2 million of them. So we're still talking about these things. The only new thing about this slide is these fibers are connected to the brain in 2 positions. The first position is here, called LGN. Even biologists call it LGN because it's just too long to pronounce. LGN, and then the signal will go to LGN and connect to the cells there. And the cells there receive the signal, and then the cell will send out new 5 cables to another part of the brain called the visual cortex in the back of our head, right? So now it kind of doesn't matter. For the interest of time, in fact, let's forget about this slide. Now, it's a very sciencey slide, right? You probably know that Leonardo da Vinci, right? He's an artist, but at the same time, he loves anatomy, right? He loves dissecting dead people and make wonderful drawings in his notebook. He is very, very obsessed with how the eye is connected to the brain, right? I guess as a painter, he's kind of mystified by the secret of image formation. So, in fact, our understanding of this on this map, how the eye connects to the brain in 2 positions, actually came originally from him, but most of the understanding came from the past 50 years of research, right? When technology catch up with Da Vinci's imaginations, and we can look at things by microscopes and kind of electricities and things like that. So, but this is a very, very sciencey slide, but I only want you to notice one thing. And the thing is, this cable will give you positions, right? Ganglion cells, position of the ganglion cells in the retina, and whether it's on and off, and the signal. Each line register a zone, a position in the retina. So each line will be connected to the first place called LGN. If you destroy this place, you're blind. Then you will have another cell connecting this cable to the visual cortex, V1. the primary visual cortex. If you destroy this part, you're blind. The important concept I want to tell you is, just like switchboard cable for telephone operation, each cell, each ganglion cell, the cable sent out by each ganglion cell will be connected to a specific cell in LGN. A specific cell in that LGN will send out a specific cable to a specific layer of cells in V1. Meaning that whichever receptive field excited by the light, there's a corresponding responsible reflective field in your brain. Right? That's the only point I want to make. Structure and function. The structure in the eye, there's a corresponding structure in your brain for that structure. If you destroy that one structure, you will be blind in that region of your vision. Right? Now, how do people know that? So this is actually an interesting paper published only last year. So this is the visual cortex of a mouse, the back of his brain, right? And this is the image shown by the mouse, right? So the mouse is kind of sitting there eating popcorn and looking at these things. And the scientists, and it's a pretty new papers, and this technology is awesome. They can actually use a microscope to see fluorescence. And if the brain, different regions of the brain are excited, it will give you a light signal, right? So this mouse has his head open, but doesn't care he's a mouse, eating popcorn, and then there's a microscope looking at the brain to look at the regional change in color that responds, that reflect the regional change in excitation. So this is the result. So you can see that if you change the spot, right, this spot will cast the light on the retina, and there's a corresponding change of activities in the visual cortex in the back of his head. That's what I said. The position cable linked to LGN, and then basically travel actually almost 10 centimeters, but the exact position of the ganglion cells for that respective field, we still know that, right? So now, most of what we told you about how we sense signal in the visual cortex, the back of the brain, came from these two scientists from Harvard, and they revolutionized the field, and in fact they got a Nobel Prize in 1981, and not that we care, but so basically these two person is the first group. They're also very, very good friends. They work together to almost single-handedly or four-handedly dissect the pathway responsible for image perception in the brain. And the animal they use are cats. So in fact, what they have done is they will get a cat, actually a kitten, very, very small cat. They will inject the cat with a kind of, how do you call this? You inject something you can't move. What's this?
Antisexual?
Huh? Antisexual. But then it's still awake, right? So basically you just can't move. It's still aware, it's still conscious. And then you just crack open the head. So of course the cat will die, right? But it's a cat, we don't care. So we crack open the head, right? And then the brain is exposed, right? This is the head. This is the head. They will use also drugs to dilate the eyes as well, so that he won't fall asleep. He won't even be able. He weren't even able to close his eye in protest. So basically, this cat is sitting in the lab, right, with the head open, and these two scientists will have very, very sharp chopsticks, right, very, very sharp probe. You remember I said nerve cells send out signal by changing by electricity, right? Not the signal, not the strength of signal, but the frequency of firing. So the probe, very, very thin wire, can actually detect this firing, the frequency of firing. And they will connect this kind of probe to a loudspeaker. whenever there's a firing, there's a click sound, right? The cat is still alive, and the cat is kind of sitting there in front of a projector. In fact, it's kind of not unlike you and it, right? This projector, but then you're not a cat and your head is not open and you're not anesthetized. But then, apart from these differences, it's the same, right? And this projector will show the cat different images, of course very, very simple images, so that we know when the cat sees different images, which part or which groups of neurons are firing differently. And I would like to show you the kind of typical data. This is what the cat sees, right? And then once again, you will see two kinds of images, right? It's kind of fast, but I hope you appreciate that they're showing the cat two kinds of images. One image is white, one image is black. Why is it like that? Because there are two kinds of ganglion cells, right? The off center and on center. What they're trying to do is to excite the off center and the on center ganglion cell on the retina, but they're not detecting the retina, they're detecting the brain. Right? And whenever there's a click, it means that and the probe is very, very thin, so that they can actually detect the firing of a group of neurons in their brain. Not the entire brain, but a group of neurons. Because that groups of neurons are responsible for a group of ganglion cells, and the group of ganglion cells are responsible for a group of reflective field. So you will see the click only when the line moves to the right reflective field, right? That's kind of the data they got, right? That's the basis of the experimental design. If they got this to work, if they got the cat to cooperate by force, then they can play with a lot of variations, right? They can change the angle of the line, they can change the shape of the line and see what happened. A lot of this kind of sciencey work, I'm a scientist, we actually not very smart, right? We will cut open things, right? We will kidnap cats, and then mainly we will just play and see what happened, right? See what curiosity took us. Their curiosity gave them a Nobel Prize, and in fact they discovered something really, really amazing, totally unexpected in the visual context of the cat. By the way, we use cats because it's difficult to do this kind of experiment to humans. And mice are too small, so cats are the easy victims. They discovered three very, very amazing types of cells in the brain. If you understand this on-center and off-center ganglion, you will probably understand what I'm going to say next, because these cells are also called ganglion cells, but they are much kind of mystic or amazing than these ganglion cells. I will tell you the simplest one. In fact, the simple version is so simple that it's simply called the simple cells, right? So it's V1, meaning primary visual cortex, simple cells. So now I told you that the ganglion cells more input than output, right? By doing that, the output actually collect multiple signals from input and do simple calculation. This kind of computation continues in the visual cortex. The ganglion cells, each ganglion cell collect input from the field, a field of photoreceptors on the retina. This cell is in retina, and then these cells will go to the brain, and then several input converge into one output. And this output is called simple cells. They also fire, right? But then their connection is in such a way that these simple cells will receive signal from ganglion cells that are aligned. The ganglion cells whose receptive fields are aligned in a line, right? So now you can see that each circle is a reflective cell responsible for one ganglion cell in the retina. In a way, each circle represents a concentric gradient of light intensity in that zone, right? But now if you have a large number of circles lined up together, this center becomes a line, right? From a spot to a line. So now, just like the ganglion cell in a retina, the simple cell is also a computer. These simple cells will not fire unless this line is at 45 degrees, right? So, in fact, there are different simple cells in our visual cortex. Different simple cells are responsible for different angles, right? So now you're from patches of gradients into a shape, right? I will show you. I have a slide, but I took it out because of time. But anyway, now this is exactly what I said, right? Concentric circles line up. Each concentric circle is responsible by one ganglion cell. This ganglion cell sends the signal to a simple cell. So now this rod-shaped, elongated respective field is responsible for one simple cell in our brain, right? So now, if this line formed by the center of respective receptive field is vertical, firing. If it's tilted, less firing. If it's horizontal, no firing. Now, I told you some cells are fired at 45 degrees, some cells 0 degree, some cells horizontal. There are many simple cells, just like a retina. This kind of overlapping fields are also overlapping. So now, these cells are firing in response to the angle of a line. There's another cell, right? So this is kind of the basic concept. So these two scientists discovered this first, so that it's the simplest way. So how about a more complex situation? And they found actually cells that behave in a more complex way. These people are not very creative, so they just call this complex cells. Good. Anyway, more complex. And this time, once again, they are a complex one cell collecting information from multiple ganglion cells. The receptive fields of these cells are lined up, right? So that the center forms a line. But this cell won't fire or won't be excited unless this line moves, right? And the amazing thing is, this particular cell will only fire. So basically, without line, there's kind of baseline. When there's a line, there's a strong signal. But the signal only these complex cells are excited only if the line moves at 45 degrees, right? So the first simple cell, it fires whenever there's a line, but it only fires when the line is at the right angle, is a correct angle. These cells won't fire even if there's a line, if the line is stationary. It only fires when the line moves, but only moves at a particular angle, right? There are different complex cells in the visual cortex. Each cells are stimulated by different angles of movement. So, we can actually show you. We can. So basically, moving signal is actually from a cat, right? Whenever you hear the sound, it means that the cells kind of excited. Moving, and actually this is the group of respective field because it's only sensing a small group of complex cells. So basically, it's moving because it's a correct angle, and if towards the end of it, you change the angle, right? It's still a little bit signal, change the angle, almost no signal. Change the angle, no signal at all, right? So, Dr. Hector has an artwork. Once again, he showed it's called uncertainty principle. in which we use a filter to summarize or condense a movie, complex movement, into lines that move in a particular angle, right? When I look at this work, I spend a long time at this work, and I can see feel all the hair in my body stood up, right? Because this is exactly the demonstration of how complex and simple and complex cells in our visual cortex works. Our evolution kind of drove us to become more sensitive to edges and lines, because these lines who's running to eat me, or our potential mate who's going to have a lot of babies for me, they kind of come as a shape, right? And I better be able to distinguish between a line and my wife, right? Otherwise, and this kind of lines and the line shape form by lines, right? And a woman is kind of a woman, has a woman lines. So we were hardwired in our physiology to look at lines. Now, there's another thing called hypercomplex cells. These guys, they're not very creative. Hypercomplex cells are one more step more complex than complex cells. So this time, it only fires when there's a line, but it only fires when there's a line, and this line is moving in the right angle, right? But it's got a really interesting twist. And the twist is, it will only fire, or it will fire more if the line is not continuous all the way across the field. But if the line has an end in it. So if there's a line with an end in it in the respective receptive field, this cell will fire. What are lines with an end? What kind of things are lines with an end, right? It's not a continuous line with no end on two sides. What are the lines with ends? Lines with ends are corners, right? Hypercomplex cells are cells that are hardwired into our brain to sense corners. We have lines of correct angles, we have movement of lines, and we have movement of corners. These are the things that we can see in our brain without us even knowing it. Because our computers in the retina and in the back of our head are doing all the calculation simply by connecting wiring and simply by kind of chemistry, right? So now, if we understand this, we have V1, primary cortex, which sends you edges and lines, and then the signal from primary cortex will go to secondary visual cortex, and basically 4 layers of neurons. We don't have time to explain to you how the other layers of information works. In fact, apart from V1, there's we know very little about how signals got further integrated in higher level of visual sensing. Our understanding today is kind of limited to V1. In V1 primary cortex, the 3 kinds of cells we know pretty well. But we kind of think, we mean science, right? Other scientists. Scientists kind of believe now that the kind of data processing follows the same principle. The details may be different, there may be other cell types, but this kind of convergence of information, and then you add meanings layer by layer, is more or less follows the same principle. There's a word in engineering called emergence. I don't know if it may not be engineering words, right? Emergence means exactly that. By processing data further and further, you get more and more complexity, and the part of this complex information is more than the sum. So this is exactly what's happening. So from lines to shapes to faces and objects. And of course, this kind of a higher level of information, the information is kind of connected to other part of the brain, right? For example, the lion is coming, I see it's lion, but if I'm not moving, then I'll be eaten. So therefore, by evolution, there's a very, very strong need to connect visual information to movement, body movement, right? There's also information sent out to our consciousness, for example, memories and that sort of things. I need to kind of remember that's the woman, right, who mated with me last spring, and I will find her again. So basically, memory and movements. This kind of high level of consciousness are important in the whole thing. And therefore, if you ask me where is the organ for visual perception, I would say I don't know. Definitely not just the eye. Maybe even more than visual cortex. Let's say the whole brain. The title of the lecture is our brain is actually doing all the seeing. Is it okay? We can go for lunch now, or I want to tell you one more thing. It will just take 1 minute. Lunch or one more thing? Lunch? Okay. So, I would like to tell you, so basically so far today, we have talked about like from the eye, right? From this solar panel, all the way to seeing lions and shapes and faces and consciousness. As we progress to the upper layer of data processing, the less and less we know about the chemistry and structure. But there are actually scientists who came from the other side, from the other end of psychology, and look at how images evoke emotions and try to work backwards towards cell biology and chemistry. So far, the approach we take is from the airport to the hotel, but there's actually some people who start from the Instagram pictures and work their way back to which city, which hotel, and which airport, right? I don't know anything about the other side because it's something to do with psychology and kind of consciousness and perception. I will just tell you one example that will illustrate the approach these people have taken. Is it okay? Okay. In the year 1994, there's a very, very interesting paper in the history of in history of psychology, mental illness patient provide a depressing, sometimes devastating, but at the same time very interesting case studies that give us a glimpse on how our brain works. And this 1994 paper illustrates this point. Throughout history of psychology, we encounter many well-known patients, right? And they are always summarized by 2 letters because we're not allowed to know their names. This example is also like that, and this patient is called SM. SM is a woman. We don't know how old she is. We don't know where she came from. Her identity is a kept secret because of the medical profession. But she's one of the most famous. She's still alive, and she's one of the most famous psychological case, medical marvel in present day. SM is a normal woman, normal person. She has a normal life. She can work. She feels happy. She feels sad. But she has one handicap. This handicap is she cannot feel fear on other people's face. Right? So basically, she's a normal person until she goes and see a movie, a horror movie, when other people are dying and crying, and she said, what's the point, right? That's her handicap. And see, it's very, very interesting, right? So her case she's still alive, and in fact, even today, there are papers coming out, even today, or this year, about her. She's kind of collaborated with a lot of kind of biologists and to study what's happening to her brain. She cannot feel fear on other people's face. in this paper, 2005, so it's like 10 years after her case was brought to the attention of scientists, one group of scientists decided to look at how her eyes move when her see people's face. You probably know that one of the things we can do, but CCD camera can do, is our eyes are continuously moving. We don't know it, but our eyes are continuously moving, scanning the reality to form an overlapping images. And our brain is condensing these pictures into one kind of global assessment of the environment, right? So kind of eye movements. So scientists believe that, so basically this SM, this is control. In this case, NC means normal control. But what's normal, right? Anyway, control. And basically they showed these two people faces, and you can see that these faces are people expressing different emotions. And basically, I think fear, anger, and sadness, and things like that. And then the red lines register the eye movement, right? It turns out that, and we didn't know it ourselves, our body is doing it without ourselves knowing it. When we see a face, our eyes are actually moving around the face, right? And the main kind of focus of our eyes are the eyes of the people we meet. When we see a person, we look at their eyes first, and then a little bit about their nose, right? What happened to SM? Look at how her eyes move. Her eyes doesn't move, right? So this is the face of the photo. She just look at the center of the field, right? Her eyes doesn't move, right? So now it turns out that this is actually the kind of digital data visualization, right? So this is one of the faces in the previous slide, but the brightness of the detail register the time spent by the eyes of control or SM on that face. If that person spent a lot of time collecting data from the eye, then the eye is brighter, right? So it's basically Photoshop and data visualization. But look at SM, nothing, right? So look at control, we actually look at the eyes of a stranger more than anything else on their face. But I told you, SM can feel happiness and sadness. It's fear. Fear is the only emotion on a person's face SM couldn't feel, couldn't perceive. What does that mean? Does it mean that the fear of a face is only conveyed through a person's eyes? Right? Does it mean that? So this scientists have done an experiment, right? And this experiment is they will so basically it takes some time, right? Once again, science. We love these kind of bars and error bars, and but it doesn't kind of matter. What matters is the psychologist will give a control and SM a number of photos, and these photos are photos of a face of a human being, and this person expressed different emotions. And they categorize this emotion as two groups: anything other than fear and fear, right? Happiness, sadness, boring, boredom, other than fear, and this fear. And now they ask the control or SM to guess whether I think this person is happy, sad, or fear, right? So, and the accuracy of guessing is this bar. If the number is 1, it means 100% correct. If the number is 0, it means there's nothing close. The control person can guess about 90% right? So control person gets 90% because we sometimes cannot guess, right? I guess when I look at my wife, I guess maybe 10% right? But so he's doing good, right? 90% right. And amazingly, if you ask SM to guess the emotion of the people in the photo other than fear, almost 90% right? If the photo is fear, the control 90% right? But SM, 50% right. 50% right means she's guessing, right? 50 is like flipping the coin. She's guessing. Now, for SM, there are two kinds of data. It's called SM3 and SMI. SM3 means you show the person, you show SM the photo, and ask SM to freely look at the photo for a limited length of time, but you can see anywhere on the photo she likes. SMI means they will block the rest of the face and only show her the photo. She can't see anything else but the eyes of the person in the picture. So if you do SMI, 90% correct. It means that if SM, she's fine. Her problem is she's not moving. Her eyesight is not moving. If she have nothing else to look at, if the person's eyes is the only piece of information she can get from the photo, she's as good as a normal person. It turns out SM, this person is a medical marvel because, in fact, SM is born with that. She's also very interesting because she not only couldn't register fear in a person's face, she couldn't feel fear herself. It's probably related, right? Something to do with learning when you grow up. She has no fear. There's another interesting paper only published this year. They put a spider on her hand and a snake, and she would touch it without any fear. So, what's happening to this woman? It turns out that she's got a very rare genetic disease in which one part of her brain was damaged. And this part of her brain is this one, labeled as green. It's called amygdala. And it's the only part in her brain, in a bigger structure called hypothalamus, that's damaged. And that's little kind of a part of the brain that looks like a pea is the part that is responsible for the perception of fear. So now, what I want to tell you now is really the end because we have to, right? What I want to tell you is the entire brain. This part is not even close to the visual cortex. The entire brain is working. When you see a photo, when you see a lion, when you see a future mate, the entire brain is working, not just your eyes. So, unfortunately, this is all we have time for. So far, I hope you find this mildly interesting. In the past 1.5 hours, I told you actually 6 things, right? I told you about these cells, solar panel, photo collectors that can collect one photon, the smallest unit of light. I told you how ganglion cells summarize pixels into gradients. I told you how one cell in the retina is connected to one cell in the brain, right? I told you how this kind of higher and higher layer of data processing will process from pixel to patches to lines to corners to movement. I told you that the system of data processing is more or less the same, so that you can recognize image, complex image. And I told you also that there are regions of our brain that can process a complex image and translate the image into an emotion, right? So I said there are 2 things I want to achieve today, right? Everything I told you about is not important, right? The important thing is what I'm going to tell you now. All these things, we are born with it. All these things, all these complex things are hardwired into our genes and cells and molecules and anatomy. We are born with it. We don't need to teach a baby how to learn fear and how to see love on his mother's face and how to see anger on his father's face. It's all hardwired into our systems, and is kind of constructed through millions and millions of years of evolution. So life is pretty amazing, right? Today we talk about vision. Tomorrow we can talk about hearing. There's another story, right? Next week we can talk about running, and every small things we do in our daily life, I can give you a lecture like that to give you the message again and again and again that our life, our body is really, really amazing. It's a machine that is kind of shaped by billions of years of evolution, and everything is so clever. And we can't even begin, or we are starting to begin to appreciate the complexity between structure and functions. And now, if you say that a scientist said, I understand this, right? And then, although I don't really understand everything, but then I think I understand enough to change the system by genes and by gene editing so that I can create a Superman, is a crazy idea because we are only beginning to understand how this works, right? DNA, these visual things, we have no idea how it worked 50 years ago, right? Linda said our school is 20 years ago, right? When this school was built, most of these things are not even discovered, right? And now to say that we are ready to change the systems to make better human beings is both stupid and arrogant. And this is the last point I want to make. And thank you so much for staying for today's lecture. And this is what we have time for. And thank you and goodbye.
We have some time for questions. By the way, I'm Hector and I teach at the School of Creative Media. I made some of the works that you were so kind to talk about. Linda has to go, so I will take over the Q&A section. So if there are any questions or comments, please.
I just well, thank you for this. I just was reading the final exam from the essay. So the amygdala is hurt in some way, or it's not functioning. What's fascinating is why it stops this woman from using her eyes only when she sees fear. I mean, that's sort of what's hard to understand. She would use them otherwise.
No, I think I've done a bad job in explaining this. She stopped scanning the eyes of human face, no matter what emotions are. Right? So no matter what photos or what emotion, he keep looking at the person's nose.
I see.
But looking at the nose is already enough for her to interpret other emotions.
Okay,
but fear is conveyed only through the eyes.
Got it.
That's the key point of that paper.
Right.
And
She doesn't scan at all.
she doesn't scan at all, and he's a very equal opportunity non-scanning. But this lack of information only handicaps her detection of fear.
Right.
Meaning that, so a lot of people, psychology, in the history of psychology, there are many of these famous patients, right? And we know her condition, we know which part of the brain is damaged, but the value of her work is to show us, give us a glimpse of how we detect fear, how normal people detect fear. And interestingly, we are scientists, right? We are monsters, so we can take a mouse and we can purposely destroy this amygdala. Of course, we can't ask the mouse to detect fear on other mouse face, but in those experiments, the experimental mouse, they also show no fear in their behavior. They also did it with a cat. So the cat, if you handicap this part, the cat in charge of the dog, they become fearless. So this part, this little dot, I think there's some Greek mythology based on that, but it's actually more important than just fear detection. But in general, high level emotion, this part is important.
Yeah, I have a question. If it's true that we see in the same way, what's the role of culture? What kind of role culture plays in the way we see? Because to what I know, like there are some people seeing in a different way and some others seeing in a different way, and how those two, like from a physiological point of view, we all see in the same way, but at the end we see differently.
Yeah.
And how is it possible to make sense of this?
It's a wonderful question, and first of all, I'm kind of not in the field of behavioral physiology, behavioral science. So basically, I'm not qualified to answer the question. With whatever I know, there are actually some similarity in how people from different culture appreciate the world. There are people said now different people see differently, right? Beauty is on the eye beholder. What eye beholder? Eyes of beholder. It's definitely true to a certain extent, but there are scientists who actually work on that. For example, there's so basically now, how about I see a photo of a beautiful person, right? And then I see, oh, this person is so beautiful. And then I see a person really ugly, right? And then, so this kind of a very cultural judgment, right? So the following experiment has been done. So they produced 4 photos of a person. I don't know what the photo is. It's not showing me the publication. But different, let's say, in a politically correct way, they're all beautiful in different ways, right? But commonly judged as being very beautiful to being very ugly. That's our judgment. And the scientists asked people in the city, in that particular paper is in Warsaw, the European city, asked people in the street to rank these 4 photos according to their beauty. So 1, 2, 3, 4. And then they flew to an island called New Guinea, out of Indonesia. There's a kind of still primitive, although it's not a good word, but anyway, there are people who have not seen the outside world until the 1960s. They were not discovered until the 1960s. And now, of course, they watch TV and anyway, it's a different story. But this team took these 4 photos, went to this place and asked those people to rank this photo according to their attractiveness. The interesting outcome is their disagreement. The disagreement is on which one is the most beautiful. But both people, European and New Guinea people, agree on the photo that's most ugly, right? So what this experiment, and this experiment has been repeated by several other groups, right? It's not just one-off observation. There seems to be a common agreement on judging what sort of body or face is attractive. And it kind of looked back to Charles Darwin, his evolutionary theory, natural selection. And he has a chapter called sexual selection. Basically, evolution is about like you are more suitable for the environment, and then you have more offspring, right? The offspring carry your genes, and then you all know that natural selection. Evolution is all about sex and murder, anyway, right? So basically, you are more suitable, then you have more sex, and then you have more offspring. Other people's offspring start to die, right? That's the concept. But for human beings, we are. So for other animals, we have they will develop beautiful feathers and then things that will show their genes through their appearance, right? So that mating selection can happen. I want, even though I got very good genes, but I want the parent of my children to have good genes as well, because our offspring is kind of mixed by her genes, right? So therefore, when I see a person, my DNA, my evolution, my animal motif is working on my brain, because every person is a potential mate, right? When I scan their faces, I need to quickly draw the conclusion, because before I ask her out on a date, that how healthy she is. Is she going to be a good mother? If she's fertile? And human beings are wearing clothes. Our face is the only information we can get, right? And therefore, that one split microsecond, I have to judge from her face about all these questions about mating success, right? And therefore, this kind of, and it's really, really important for the survival of my gene. So therefore, this kind of instincts hardwired into our brain. And now people say that symmetry of the faces and these sort of things are universal in judging attractiveness in spite of your culture. So there seems to be two types of perception. Something is core, common to humanity, and something is developed in different cultural context. Okay.
Maybe I have a question. Again, like I said, it was wonderful.
Totally inspired by your artwork.
And I noticed that you, throughout the book, you compare the human brain with machines. So at one point you talked about the human brain as kind of switchboard operator. You also talked about the brain with computations. Are those just metaphors? Or to what extent, for example, do you think the brain really is a computer?
It's an interesting question. If I give this talk to science students, I won't use this metaphor. When I give the talk, I'm always torn between, is it boring, or is it too much information, or giving a talk on this subject to the general public give me a lot of pressure, right? And this pressure stimulated me to constantly looking for metaphor for the general public to understand. But the interesting thing about this is that using machine as a metaphor for biology. If you look at and this is very, very interesting, right? I didn't decide to do that. I select this metaphor during the preparation without research or without too much consideration. I just choose it for being clear and funny, right? But if you look at a lot of 19th century discussion about biology, if you look at the drawings, they will, I don't know whether you've seen those drawings of a brain divided into different rooms and there are little small people working, right? It's a factory. I don't know whether you've seen photos about the heart, right, as a pump, right? And there's a steam engine, right? So in 19th century, the most advanced machinery are steam engines, right? And therefore, people use steam engines to illustrate the body. Today, the most advanced thing are computers and artificial intelligence. So I use computer as a metaphor. I think there's always a drive, and I don't know where it can come from, to use what perceived to be the most advanced things in technology as a metaphor for human beings. And I think it comes to my last point, that life is so amazing that our body, the design, the nanostructure, from nano to macro structure, are so amazingly designed, but we're not allowed to use the word design, so amazingly constructed that it rivals the best machine that can come up by human beings, contemporary human beings. So now we are talking about artificial intelligence and loading our mind to a machine. Maybe 100 years later, machine is already outdated, obsolete things, and we'll be using different metaphors, engineering metaphors to describe our body. Our bodies are always better than engineering. So, and this kind of come back to our idea, right? We're talking about gene editing and CRISPR, and once again, if you look at all these articles, newspaper articles, to explain this process, they're also using computation languages, right? So we are almost like in the crossroad of trying to understand the body, and at the same time worshipping the body by comparing with the best thing we can. I think in the absence of God, this is the best we can do. Not good.
Well, push that further then. So does the computational metaphor actually provide a superior form of explanation than say a hydraulic metaphor? You spoke of water and flows of water and so on in some of your thoughts. It wasn't the dominant metaphor you used. But is it actually, so is the computational metaphor actually, could it be characterized as a superior form of explanation? Or is it merely another form of representation, another picture?
I think what we're talking about is me, right? Because I
To
think
you.
this talk is to me, right?
Yeah.
I think it's driven by my desperate attempt to sound cool. That's the explanation. But then I understand your question. Right? There must be something behind this, almost like collective ideas of using machines and to represent human, represent biology. It is undeniable that our neurons work using electrical signals and have long wires that connect one part to another. Using cables and computation engineering terms are inevitable. If I'm talking about bacteria physiology, then probably I will be using metaphors on programming, but not the hardware. So I think the subject matter design a little bit, but why programming? And why wiring, right? And I think that's because in my consciousness, it's cool. It's a cool and advanced thing, and it is the only thing that rivals the beauty of our body. So, is it anyone want to kind of comment on this?
It's not just a metaphor that you use because you find it cool. It's a metaphor that I think is very dominant in our culture. So I think that these questions are very relevant in terms of whether we think that the mind is really a metaphor or not. A lot of philosophers debate those kinds of questions. So I think this is why these questions are.
Yeah, but then 100 years ago, before computers was invented, people also use metaphor, right? But they use different metaphor. And my observation is they always use an engineering metaphor, and that metaphor is the most advanced and coolest machine at that time. And before machine was invented, we used mythology, right, and God. So we always use something that we think is cool, but don't really understand to represent human bodies, and I think it reflects our kind of, I don't know, maybe a little bit humbleness. I don't know, I'm just a scientist. It's just difficult for me.
Alright, this is only the first of a series of lectures which is organized around the Art Machines Conference that will take place in early January and the Algorithmic Art Exhibition that will take place in late December at City Hall. So please look at our website and